How often do you provide students with a blank sheet of paper to record their own personally meaningful representations? A 2002 study discovered that worksheets continue to predominate in most classrooms and that they often do not provide opportunities for children to express their own informal thinking of the task. Very few teachers in this study kept any records or student samples of these representations to show how they evolved over time. There could be a number of reasons for this. Perhaps the research community has done a poor job of communicating to teachers how important these representations are to children's mathematical development. Perhaps it is unclear to teachers how to use these representations to gain any real useful insight into learners' mathematical development. And of course, the very real likelihood that curricula often is not set up initially to foster this kind of development. The Common Core authors clearly value representations. You can see here how extremely prevalent the idea of representation is in the Common Core operations and algebraic thinking domain. Analysis of these standards illustrates that representations are used in a number of ways, used as a part of a process for solving problems, as a means of communicating conceptions of addition and subtraction, as a tool for recording their work. In their well-known book, Classroom Instruction That Works, Marzano et al. Were very clear about the role of representations in the learning process. Notice, however, in this quote, that for children to get the goodie out of a representation, it has to have been generated out of their own thinking. The process of taking one's own thinking, which is often messy and ill-formed, and trying to put it into some kind of a representation, which is packaged in a way that it could be clearly communicated to others, this process requires individuals to make sense of the knowledge. All too often, however, classroom instruction is focused on getting students to produce a desired end product of instruction, rather than allowing for the time that it takes for children's thinking and their personally meaningful representations to develop. And as I mentioned before, this is very likely due to the fact that most curricula is not set up to allow for student representations, so for it to happen pretty much has to be a consciously chosen instructional decision on the part of a teacher to incorporate that element. In the Progressions document, the Common Core authors describe the role of representation as a tool for problem solving, and they specifically name it as a means of integrating mathematical standards of practice. They expressly name Mathematical Standard of Practice 4, Model with Mathematics, and Mathematical Standard of Practice 5, Use Appropriate Tools Strategically, as ways in which representations can be used and developed. Furthermore, they talk about the advantage that these representations offer in supporting children as they seek to mathematize real-world situations and as a tool for reflecting on and discussing mathematical concepts. Now, these advantages are only able to be realized if representations play a pivotal role in instruction, where they're used to make sense, used to compare different representations of the same thing, used to justify one's solution and solution method, and used as a source of dialogue about mathematical concepts. In this lesson, we will primarily be focused on student-generated representations, and then in the next lesson, we're going to extend this by looking at the role of the teacher's use of representations in fostering students' mathematical development of representations into more abstract forms, leading eventually to meaningful facility with equations. Now, many of the ideas in this lesson generate from Worthington, a researcher of early childhood math representations and a co-author of the book that you see at the top, as well as from Wittek and Ennis, who have written the professional resource you see at the bottom of the page, specifically designed for teachers of pre-K through second grade on the topic of representations. Part of what makes studying representations difficult is that there are various aspects to representations. In a way, you can think of it as both a noun and a verb. In a classroom environment which honors children's informal and prior knowledge, children build representations which are the direct result of their current mathematical conceptions. The process of building those representations is the verb component, and it is as important as the end product, or the noun, which usually takes the form of marks, drawings, pictures, or symbols. This child should then be able to use this product as a tool for communicating to other people the thinking that he has about this situation or task. These types of representations are truly representative of what a child is currently thinking mathematically, and they become a wonderful tool for formative assessment. Now, this is not true, however, if the representation is the result of mimicking something that someone else has asked them to do. In that case, it's very hard to use it as an accurate assessment because it's unclear to what extent they've effectively learned to mimic as opposed to effectively learned to understand. All too often, we can be misled by tasks where children are mimicking our expectations. Young children have various ways of representing their mathematical conceptions, and we can classify the various elements in their representations as pictographic, iconic, or symbolic. The first types of representations typically are pictographs, and in the top image you will see the situation illustrated. So there are two people at the table. Each person has 3 cookies. How many cookies are on the table? This girl has even named who the 2 people are that are at the table and has faithfully drawn the cookies that each person gets. They're so clear that it even looks like chocolate chip cookies to me. There's no numerals. Pictographs may play a role for quite a long time as children, young children, typically think through images. Over time, they learn to think with symbols, but it's going to take a while before that becomes their default mode. Iconic representations are similar to pictographs, except they use a simplified indicator of the object rather than drawing the exact object. So instead of cookies being drawn, maybe it's dots or tallies. And iconic representations are then something you might want to foster because they're easier to draw, less time consuming. They represent a step, therefore, towards efficiency, but also towards greater abstraction. Because a dot is not a cookie, a child has to do a slight amount of abstraction to reach that point where this could symbolize that. Finally, symbolic representations are used spontaneously by children when they come to have particular meaning. Now, what I mean by that is that if you really allow children to do their own representing, they tend not to use symbols until the symbols have meaning for them. They tend to use representations that have meaning for them. The only exception to that is when they think that you're expecting that they have to do that. But in that case, it's harder to tell whether they're truly understanding it because it's not spontaneous, it's prompted. In the problem at the bottom, the child knows that 10 and 10 makes 20. She not only recognizes that mathematical relationship is advantageous for solving this problem, but she also understands how to communicate that relationship clearly in a symbolic form as a means to justify her solution. If we're willing to allow children to use their own forms of representation as a means of making sense and communicating their thinking, they not only support the child's mathematical development, but they also serve as wonderful formative assessment tools, which can give us some insight to where they are on that developmental spectrum. So we're going to take a look at some examples of student representations and what we might be able to learn about them through a sort of formative assessment. This problem was one of a series of problems that the children were given after reading a rendition of Jack and Jill. There are ordinal numbers such as first, second, third, which had been recently studied in the class, as well as cardinal numbers present in the problem. So the children really had to make sense of relationships. It wasn't an option to just pull out numbers randomly or they would have an incorrect solution. I see this child using pictographs to represent Jack. And the pails, if you look at the first pails that are drawn, they actually look like pails, including even a handle. But notice how the drawings of the pails start to become more generalized until the last one is just a box. This is interesting. It illustrates a shift towards an iconic representation, which is something I would like to see her develop as a more efficient method. So this work shows me that I might be able to shift her towards that goal by giving her problems with slightly greater numbers of objects and with objects that are a bit tedious to draw. She's going to be ready to go towards something iconic based on this picture. Another aspect I find particularly noteworthy about this work is the level of organization used to communicate her thinking. She has each trip neatly summarized and labeled and organized on her paper. And finally, I see that her answer includes both a numeral component and a word label component. Those are very noteworthy in terms of her capacity to communicate in a representation. Worthington's research into children's earliest mathematical representation shows several developmental components which occur between the age of 1 and 8. Children entering kindergarten may or may not already be exploring symbols, which you see there in the middle, but this should definitely be something that is actively fostered in school. As the children experience effective teacher modeling over time, which is the topic of our next lesson, they will also very likely begin to attempt to incorporate symbols to represent operations as well. These classifications that you just saw on the previous slide are useful in analyzing student work. In this kindergartner's work, I see that the student is using iconic representations because the problem is about boxes and the student drew circles. I wouldn't think boxes are difficult, but apparently for this child, the circles were easier to draw than the boxes. I see this child using numerals as labels for quantities, so that means she's in that exploring symbols phase. I don't see her using any symbols or any attempt to represent the operation that's being involved, though. I see her labeling with the numerals as a means of communicating her answer. But you don't see any evidence that she's seeing this as a group of 7 plus 4 plus 3 in any kind of a symbolic way. Now, another important aspect of representation is student explanations. The end product of a representation, which is what we've been looking at, can be very insightful, but having a conversation with the child where they tell you what their representation means to them and how they used it to communicate their thinking is even more valuable. When I examine these two representations, I'm immediately taken with how similar they are. Although the first child has a reversal in her communication and writes 18 like 81, that's actually pretty typical at this age, and we're going to discuss that in PD Module Part C. But other than that, it appears that the two representations are almost identical. So does that mean that the children's mathematical thinking is the same? Let's find out what they have to say about their work. The first child describes pretty much what you would expect based on the sketch that she drew. That she drew 12 circles, then she drew 6 circles, and then she counted them up to get 18. When the second child was asked about what she did, however, she gave a very different answer. She basically reported that she counted on and didn't really do anything with the first 12 circles that she drew. Simply pointing one by one at the 6 circles, she goes, well, what I did was I said 12, and then I went 13, 14, 15, like you see here. This is a huge leap forward because to count on as opposed to count all is a significant leap. If you went through Part A module, you'll see that that requires quite a bit of abstraction. Now, that wasn't evident in her representation, so in the explanation you get to say, well, why did you do this? And the answer here is very insightful. The child thought the teacher wanted her to. She thought that was expected, that if you showed your work, it meant you had to show all of these pieces. That's very interesting because I could intervene in an explanation then and say, if you don't need to draw these, it's not very efficient to draw them. What could we do instead to help you show that you had 12? You know, and you could explore some different ways of representing that group without drawing all of them. So that's very interesting and would be completely unknown if you hadn't asked the child to explain their work. Now, I realize that explanations are not something that you can have with individual children every single day, but there are ways to incorporate this, and I encourage you to do so. They can occur regularly through interactions with students while they're doing their work. You won't get to every child every day, but you'll get over time, you'll get through them. And then also during strategy shares, you can invite students to share how they thought about it and get some more insight at that time. It's important to send a message to children that they need to make the decisions for themselves about how they're going to represent their work, rather than dictating how we want their representations to look. The reason for this is that we will only really know if they truly understand, if they're able to use that understanding to generate their own sensible representations. Choosing their own representations is also essential for the wide variation of students that you find at the kindergarten level. You will have students who are ready to start working with some symbolic representations at that next level where they're attempting to integrate them. You'll have other students who are nowhere near ready for that. So by allowing them to make some decisions about how is this making sense to me and how do I want to communicate it will allow for significantly greater differentiation. Children may benefit by using concrete manipulatives before they plan how to communicate their work on paper. So if you find a student who seems clueless about what to put on paper, have them actually use some materials first that make sense to them. What materials would help you figure this out? And once they've done it that way, say, okay, now you need to find a way to show what you just did here. How could you represent these things? What symbol would you like to use? How would you like to draw that? So doing that concrete step first can be helpful. Although the representations that we're discussing are student-generated, the teacher plays a very important role in classrooms that facilitate children's use of representations. In the next lesson, we'll be discussing how the teacher can actually be an influential role on children's ongoing use of new manipulatives and increasingly more abstract representations in a way that won't interfere with the child's sense-making approach to communicating their thinking. We have already discussed and given examples of how a teacher can use the representations as tools for gaining insight into children's thinking. During individual actions, whole group strategy shares, you can be pulling out their thinking and supporting the idea of how to build connections between different representations, especially between concrete representations and slightly more abstract representations. That connection can support everybody in your class by connecting two different representations of the same thing at slightly different levels. Finally, teachers think about children's use of representations, and they have to make some decisions about their instructional response. So let's examine what that might look like in practice. You might remember this example that was in a previous lesson where a small group of kindergartners had all just solved the following problem. 5 zebrafish were swimming near the coral reef. 6 clownfish joined them. Now how many fish are swimming near the coral reef? Let's take a closer look at the anecdotal records for a few of these students because they reveal some interesting elements about the children's representations. Notice that Amelia and Rommel both used drawings, but Amelia drew circles to stand for the fish, where Rommel drew actual fish, scales, fins, and all. This is noteworthy because using circles to stand for fish is more abstract and more efficient than drawing actual pictures of fish. So I might want to have Rommel and Amelia share their work with each other and then talk about how each of them made sense for the problem. I might then say, Rommel, I see that your last fish is pretty messy without much detail. Were you getting tired of drawing fish by the end? Yeah, I can believe it. Notice what Amelia did. She didn't need all of those details to solve the problem. Do you think you could try something like that to save yourself a lot of work? I hate to see you putting out all that effort when it works even to have something with less detail. Now I also want to draw your attention to Mario. Since 5 plus 6 is 11, he ran out of fingers, but since he only needed one more, he was able to imagine that last finger. This is a little step towards abstraction, which is why I made a note of it. Now, if this is the first time I ever noticed anything like that from Mario, I might just sort of sit on it and continue to watch. But I'm eager to see if Mario does anything like this again, because I'm really wondering if he is soon ready to start counting on, especially if the amount to be counted on is very small, like 1 or 2, because that requires abstracting the first quantity and counting on from that value. I'm just wondering if he's partially able to abstract one quantity, whether he might be able to do something like that. So those are some thoughts that don't necessarily indicate an action on my part, or might, but certainly things that will inform the way I interact with the children. While children's early representations seem very primitive to us, they actually serve an important role in children's meaning making. Having said that, as a teacher, we're obviously eager to see those representations develop incrementally towards increasingly more efficient and symbolic modes, while still keeping the child's sense-making intact. They're at kindergarten. There's a lot of mathematical future for them. We want them to still keep making sense. You can have students who are using representations that you think are on the horizon for several other students, and you can feature that in a strategy share. So if you think, I think a number of students might be ready to do this, then you can have a student who's doing that share their work and draw those students into a dialogue about it so that they can begin to see it. That's an example of peer modeling. You can also match students in pairs, similar to what I just talked about with Rommel and, what was the girl's name? I can't remember now. Rommel and Amelia, and that's another example of peer modeling. as long as the child doesn't feel that there's pressure that they need to conform to their peers' approach, but they are invited to if it makes sense to them and if it appears more efficient to them. They're invited to consider doing that. The teacher plays a very important role in children's development of mathematically meaningful representations, which also incorporate the increased use of symbolic language of math. And that is actually going to be the subject of our next lesson. If you would like to continue reading about representation, student-generated representations, these are some good sources to start. The last two sources here in particular are focused entirely on representation.